Hello, everyone. This is a recording for our Tuesday, April 28th main lecture, and we're still working on Chapter 10 material. Still talking about Chapter 10, which is our first rotation chapter of 3, Chapter 10, 11, and 12. Last time we met, we spent some time defining angular displacement, angular velocity, and angular acceleration and their relationships with respect to one another and these tangential velocities. In addition, we defined rotational kinetic energy as 1/2 I omega squared, where again, omega squared is rotational velocity, and that makes this the rotational mass, or the moment of inertia. And we actually found the moment of inertia from an analogous result, saying that this should be the rotational mass if I'm expecting the kinetic energy to take the form of 1/2 mass v speed squared, where here it's in rotational quantities. And we derived this relationship that moments of inertia are related to the sum of all the individual point masses and their distances away from the axis of rotation. So for example, we said if this is a rotational mass around this axis of rotation, here's one point mass, and it is this distance away from the axis of rotation. So m1 times r1 squared plus m2 times r2 squared. And then you do that for all the masses in here, and that will sum to give you the moment of inertia, or the rotational mass. So rotational mass depends on mass, but it also depends how far away you are from the axis of rotation. So that's what that R represents. When we move over to integrating or finding the moments of inertia of composite objects, so like a lot of these objects, you have rods that are made up of a bunch of infinitesimal masses, or spheres, thin shells, hoops, discs, or cylinders. Same moment of inertia for both, or a thick ring or a hollowed cylinder. We're going to be using integration methods to find those moments of inertia. So in that limit, mass will just become an infinitesimal mass, and this will still be the distance away from the axis of rotation. We also briefly talked about the fact that we're going to be using Newton's law in this form, and if we don't get to it in this lecture, we'll get to it in the next one, where we're going to be using Newton's second law for rotational quantities, where at that time we'll be introducing this quantity of torque, which is represented by a cross product here, but it's really a rotational force. And the sum of torques, or the sum of forces for rotation, equals m times a. The sum of forces equals ma, but in all rotational quantities here. And it's because of this we make an analogy to, it's like sum of forces equals ma. And we say that if something is more massive, it has less acceleration. We say the same thing here. Something with more moment of inertia has less angular acceleration, or rotational acceleration. And something with more moment of inertia typically has more mass farther away. And we spent some time looking at this table. So for identical masses, same mass and same radius, for example, here I have two objects, but one is a solid sphere, one is a thin sphere, and you can see the moment of inertia. 2/5 is like 0.4, 2/3 is like 0.66, is larger for the thin spherical shell, and that's because more of the mass is actually farther away, because all of this is hollow in here. And this is the same mass, same radius, but the mass is evenly distributed because this is a uniform solid sphere throughout the body. And so this guy has a larger moment of inertia, and so in theory it should rotate or it should accelerate less than this one. Okay, so I'm going to show you a couple of demos that Tyler put together for us here on YouTube. I have them ready to go though, so they're ready on our YouTube channel. And these are dealing with moment of inertia. And this first one is just looking at the acceleration of an object for, again, when masses are closer versus farther away. So if masses are closer to the axis of rotation, the moment of inertia should be smaller or larger. Smaller, right? Because the R value is smaller. And when the masses are farther away from an axis of rotation, the R value is larger, therefore moment of inertia is larger. And a larger of moment of inertia should go smaller, should have a smaller angular acceleration. So let's take a look at that.
So in this demo, which is moment of inertia, we will be hanging a mass of approximately 110 grams from the apparatus with the weights as close to the center as possible, except for this little area.
You see the axis of rotation is right through the center of that tiered pulley system, and he's going to show you the mass that's hanging from the pulley system in a second.
So we'll wind it up and look at the rate of spin. Next, we'll increase the moment of inertia by adjusting the masses to the outermost point. Using the same mass, I'll wind it back up. And now note the rate of spin, which is much less.
Okay, so pretty cool. So we can really see that in action. So again, something with a larger moment of inertia means that masses are farther away from the axis of rotation, and it also means that it spins less, or its angular acceleration is less. We're going to see that again, and let me just remind you really quickly before we start of the moment of inertia of a thin ring or hoop here versus a solid disc or cylinder here. And comparing these to one another, you can see the moment of inertia of a ring is greater than the moment of inertia of the disc. And here they have similar mass and similar radius. Well, we're going to look at a demo where Tyler's going to be rolling a ring and a disc of equal mass and radius. He doesn't weigh it in front of you. You're just going to have to believe that they're equal mass, but you can see they're equal in radius down an inclined plane. They're going to roll without slipping. And we're going to see one of them goes faster than the other. Can you guess which one?
This second demo, which you're about to see, is a demo on rolling a disc and a ring down an inclined plane. There's a disc made of wood and a ring made of metal. These have the same mass. As you can see down that roll, the disc went much faster than the ring of metal.
Because it has a smaller moment of inertia. Right? The disc has a smaller moment of inertia, it goes faster than the ring, same mass, same radius. Okay. Hey, thank you, Tyler. Oops. Okay, so moment of inertia. We're going to spend a little bit of time working this problem below, but before I do, really quickly, I did want to talk about the moment of inertia of a single point mass. So right now, we're just talking, we're not integrating yet, we're just talking about finding of the moment of inertia by integrating over a point mass distribution. So first, I think we should look at the moment of inertia of a single point mass. So here it is, m, and right now it's some distance of r away. And the single point mass, the moment of inertia, it's looking at its shortest distance between the axis of rotation which I suppose I should indicate that it's rotating around this axis with this little rotating arrow. Maybe it's going omega around it. And it's the shortest distance, r, kind of as drawn here. So the point mass for a single, or the moment of inertia for a single point mass is the sum of one, right? So it would just be m times that distance r squared, or mr squared. This is for a single point mass. If I have many point masses, of course, I'd have to put in their different masses and their different distances away. But before I do, I just want to make sure that this makes sense. I mean, I know that I say kinetic energy rotational is 1/2 I omega squared. Well, if I put in the moment of inertia for a single point mass, this should make sense and should eventually reduce to 1/2 mv squared. And you can see that it will. If I use omega is v over r, then kinetic energy rotational is 1/2 mr squared times v squared over r squared, or 1/2 mv squared, which is just the kinetic energy of a single point particle. So this makes sense. And I'm going to go ahead now and just find the moments of inertia of a bunch of different point masses, as seen below here, around different axes of rotation. So I don't know why they're squares all of a sudden, but these are supposed to be all equal masses right in here in this picture. 3 equal masses. And what I want to do is I want to find the moment of inertia around different axes of rotation. So the first axis of rotation would be here. So it would be dissecting this bottom mass right here. And so I sub 1 is going to be the moment of inertia associated with this rotational axis. And if I give little, numbers 1, 2, and 3 to these point masses, which are all the same mass, so m, and m, I would then say that the moment of inertia is just given by summing over, again, all of the masses times their distance away from the axis. So I should have 3 terms, right? m1r1 squared plus m2r2 squared plus m3r3 squared. M1 and equals m2 equals to m3. So that was a little bit redundant, but their r's can, and some of them are different. Like r1 is this distance right here from the mass to the axis of rotation. And in this problem, assuming that this is right in the center here, so that's something I would have to tell you, this is a over 2 away from the axis of rotation. Actually, both mass 1 and mass 2 are. So in my sum, mass 1 is just m, and r1 is just a over 2 squared. Well, same with r2. Oops. A over 2 squared. And mass 3, again, I keep forgetting to write those as m, is actually 0 away from the axis of rotation. It's right on it. So these are point masses right on the axes. And so if these are the same masses, then I'll have 2m a over 2 squared as the moment of inertia about axis of rotation 1, or 2m a squared over 4, or m a squared over 2. And that equals I sub 1. Well, what's the moment of inertia about a different axis? So let's find it around here. The moment of inertia around axis 2. Let me go ahead and draw that one in. So I sub 2, again, it's just the sum over all of the point masses and their distances away. So again, it would be m1r1 squared plus m2r2 squared plus m3r3 squared. But those r1, r2, and r3s have changed. Well, maybe. Some of them have. How about that? Mass 1, here it is now a distance of what we're calling b away from the axis of rotation. That's its r. Same with mass 2. And mass 3, again, is 0 away from this axis of rotation. So I'll have m1 b squared plus m2 b squared plus m3 0 squared, and mass 1 equals to mass 2, so this is 2m b squared is the moment of inertia around that second axis of rotation. So let's just look at the very last one here. Say the axis, let's say the axis of rotation is now here, and that would be our third axis of rotation, so it's called I sub 3. It's going to be the sum over all the point masses and their distances away from the axis of rotation. And here, both mass 1 and mass 2 are 0 away from the axis of rotation. And so that leaves only mass 3, which is now going to be b away. So I sub 3 is mb squared. So I sub 3 is clearly less than I sub 2, but it's hard to gauge I sub 1 because we don't have a relationship with A in terms of B. So I have this little note here that says at the very bottom, if A equals 1 and B equals 2, which axis of rotation will allow for a faster angular acceleration? Well, let's plug in some values. I1 would then be equal to m times a squared, which is 1 squared over 2, or m over 2. I2 would then be equal to 2 times m times b squared, 2 times n times 4, and I3 would equal to m times 4. So in fact, the smallest moment of inertia, this is 8m and that's 4m, the smallest moment of inertia is I sub 1, which is less than I sub 2 and I sub 3, but I sub 2 is greater than I sub 3. So this is how our moments of inertia are rated. Which one goes the fastest? I sub 1 would be the fastest if they were all experiencing the same kind of torque acting on them. Rolling down an incline, let's say that. Okay, cool. Those are the different moments of inertia for point masses. And I seem to just give myself this extra page here, so let me go ahead and cut this out and put it back on the other page. Because next we're going to find moments of inertia of continuous mass distributions like this. So we're expected to be able to find some of these moments of inertia, but a lot of times we just look them up, but we're going to be talking about how to find them. So for instance, today in lecture, we're going to be finding these two in lecture today. We're actually also going to be finding this one in lecture today too, by integration methods. In your lab, so in lab, you're actually going to be finding this one and this one in the lab, rotational inertial lab that we're going to start Wednesday and Thursday of this week. I'm going to give you a handout online how to find this one. This one we'll actually do today in lecture 2, and I'll allude to how to find this one in lecture today. So we're going to really cover out how we can actually integrate and find all of these quantities on our own. So I'll be giving you some handouts for the rotation stuff. You'll see there's nothing in that book of notes, so I do have some handouts collected for you guys. One of them will be how to find, like I said, this one right here. But actually the one we're going to do in lecture today, I have a handout for too, so I'll be giving you that as well. But let's start a little easier. Let's start by using integration methods to find the moment of inertia of, these are uniform rods. Both of them are going to have mass m and length L, and that's all we need to know to solve for the moments of inertia. I can see what the answers are, so I'll know when I'm right. And these are continuous mass distributions, so I can no longer see the spacing between the point particles, so I can't just use the simple sum anymore. So what I'll be saying is that these are made of little infinitesimal masses, right? Just like before, little DMs. They're uniformly distributed. Both of these are uniform rods. And so each one of these is a little DM. And so my mass here will become a dm, and I will now be performing an integration over dm times r squared, and r here still represents the distance away from the axis of rotation. So as a general rule, I'm going to start placing my axes at the axis of rotation, and by that I mean my axis for the integration. So for instance, let's go ahead and start with this case, the thin rod that has an axis of rotation through its center, and then we'll continue with the thin rod with its axis of rotation on its end. And so starting here, I'm going to go ahead and put my origin, so my y-axis, I'm going to put along the axis of rotation, and x is what's going to be sticking out, and this would be the negative x hat, for instance. And I'm going to integrate over these little DMs right here. And so for instance, for one of these DMs, this distance of r, this is its distance away from the axis of rotation. And that's why I put my axes here, because it makes it very easy then to say that r is equal to x, right? R will also be equal to x here. And it doesn't matter if it's positive, negative, you see it's squared in here. So a lot of what I'm doing, if I put my axis of rotation on the y-axis where my origin is, then a lot of times I'm going to be in a pretty good situation for finding this value of r, which means all I have to do is find dm. Dm comes from the density, you guys know that. And this is a one-dimensional linear density, one-dimensional linear density, uniform density. So lambda equals dm dl, but when it's uniform, remember it's mass over length, total mass over total length. And the dl, of course, just depends on the size of the dm, and here it's on the x-axis, so it has an infinitesimal size dx. And so, nice and easy, this dm is m over l dx. And so when I go to find my moment of inertia, I'll plug that in for the dm. And then as mentioned, my r squared is just, here, x squared, based on this nice and convenient place that I placed my origin. And now what matters are my limits of integration. So my rod is going to be integrated from x equals to minus L over 2 to x equals to positive L over 2. So the location of the origin is also changing the limits. And when I'm done pulling all my constants out of this integral, it will take this form. Here, the minus sign can come right on out to give me L cubed over 2 cubed plus L cubed over 2 cubed, which is, of course, just 2L cubed over 2 cubed, which equals L cubed over 2 to the fourth. Fourth, what? 2 squared, or 4. So the moment of inertia then is m over 3L times L cubed over 4, which is m L squared over 12. And that's exactly what we see here. Woohoo. You know, nothing really changes in the setup when the rod is around the end, except one thing. Can you guys guess what that is? This is a uniform rod, so does my dm change? No, not if I put my axes kind of like I had before, here and here. So here's my positive x, and I'm going to put my positive y axes on the axis of rotation here. So does my r change? Not for this value, right? R is still equal to x here because I've chosen well placing my origin. So my dm doesn't change, it's still uniform. My r doesn't change. Is this the same as before if I wanted to find the moment of inertia of a rod on its end? Well, the only thing that changes are the limits, right? That's where I've placed the origin is the only thing that's changed here. So my limits change from 0 to L. That makes this integral much easier. Oh, excuse me, guys. And here's the moment of inertia of the rod on its end. So this is through its middle or its center of mass location. Right, that was the middle. And here, this is its end. Thin rod, axis of rotation on its end, bang, versus thin rod, axis of rotation through its center of mass or through its middle. All right, so we've integrated. Pretty nice. Let's do another one. We're going to do the thin spherical shell. Before we do the thin spherical shell, I want to find the moment of inertia of a ring. Because when I find the thin spherical shell moment of inertia, I'm just going to treat it as a bunch of stacked rings. Right? A thin shell can be thought of if you stack a bunch of rings. So if I know the moment of inertia, so here's the axis of rotation. So these rings are all centered on the axis of rotation, and so is the thin spherical shell. It's through its center of mass. And again, this is also a uniform, it doesn't say it, but this is a uniform thin spherical shell of mass m and radius r. So m and r will be known quantities, that's all we need to know. But since I'm going to be stacking a bunch of rings, First, I'm going to find the moment of inertia of a single ring. So here's a ring. It's a one-dimensional object, right? And I can think about it as just a bunch of tiny little point masses, dm. In a circle, if I was looking down at the circle, of course, they would all be at some distance of r, the radius of the ring, away from the axis of rotation, if the axis of rotation is through the center, which it's going to be here. So the axis of rotation is sticking out, right here. This is a continuous mass distribution, but it's a very, very special case because r is just equal to the radius for every single one of these point masses. They're all the same distance away for a ring. They're all a radius away. And it's a constant. So this r squared will just come right on out of the integral for a ring. And the moment of inertia of a ring is then just r squared times the integral of the mass, all the little masses, which is just the total mass m, or it's mr squared. And if you go back and look at my sheet here, here it is, the moment of inertia, it says of a hoop or cylindrical shell. Well, hoop means ring, but it also can be a cylindrical shell because you're just stacking a bunch of them on top of each other effectively to find the moment of inertia of the rings. So for one ring, or even a thin cylindrical shell, which is a stack of these, of the same radius, the moment of inertia of a ring is mr squared. Now I'm going to use that to find the moment of inertia of a thin shell. And remember, I do this by integrating all of the moments of inertia of a ring. Well, the funny thing is that the moment of inertia of a ring looks just like the moment of inertia of a point mass, right? And you see, they just really look the same, except for the r is the radius of the ring. Well, if I'm integrating over a bunch of rings that are changing their radius, though, to make a shell, then ultimately it looks like I'm just integrating over a point mass, but I'm not. It's just that the moment of inertia of a ring looks just like a point mass, and that's from a high level of symmetry. Okay, sorry. So this is the moment of inertia of a ring of infinitesimal dm. So each one of these rings has an infinitesimal mass, and each one of these rings has a radius of r. So this happens to also be the distance away from the axis of rotation for every point mass on the ring. So here's my axis of rotation. And so what I want to find is dm. Dm comes from the density. Well, this is a thin spherical shell. So the shell is an area. This is a dmd area equal to total mass over total area, which is total mass over what is the area of a thin spherical shell? Well, it's 4 pi capital R squared, right? The outer radius squared. So all I have to do is find my d area, and then I can solve for dm. So if I'm making rings, if I'm taking rings and adding them up to make the shell, then I'm saying that it's 2 pi r, the size of the ring, times the thickness of the ring. But it's not the thickness of the ring as it changes radially. It's the thickness of the ring as it changes over this kind of little arc length right here, ds. Oh, excuse me. And ds is just equal to, generally it's r, oops, not, pardon me, not big R over there, it's little r, d theta. So let me draw that a little bit better for you so we can see it. So if this is my sphere, and right here at the center of the sphere, I'm talking about a ring of some thickness. So let me draw my ring. Here it is. It currently has its radius of r, and I want to take a look at its little thickness right here, ds. It is dr, my bad. This is going to be cap r d theta, so this is kind of the definition of arc length right here, and this is little inside of here. This is a d theta. So this is the theta that I'm going to be changing here. So this little arc length, ds, is going to be equal to r times d theta. Kind of my definition of arc length right there. And so the area as this thing changes, this ring is getting thicker in the integration, is 2 pi r times capital R d theta. And so altogether, once I have that, my dm will be m over 4 pi r squared times 2 pi little r times capital R d theta. One of those r's cancels. A pi cancels, and a 2 cancels. And dm will equal to m over capital R, little r, times d theta. Oh, and a 2. And so at this point, I just need to plug in something for my r squared here under the integral. My dm has made it clear to me that I'm integrating over d theta. But I have everything else in terms of this little r over here, so I need to do something about it. And so I'll go ahead and redraw this again, this circle again, different color this time, I guess. And here is my ring that I'm looking at again. Here is its radius, r. But here is the radius of the circle. And here is theta that I'm going to be integrating over. And looking at this, it looks like I'm integrating theta. I'm starting from here at the top, from theta equals to 0 all the way to theta equals to pi. And so theta equals to 0 to theta equals to pi will incorporate all of the rings to make the full shell. So if this is a d theta, this is theta. Maybe I should have drawn this up here. Here's a little d theta. Here's my ds. Same thing, really. But I'm going to integrate from 0 to pi. And once I do, I can see this triangle here is a right triangle. And so I do have a relationship between r theta and big R. In fact, once I say that sine of theta is r over big R, I can say little r is capital R sine of theta. What? And sorry, I kind of messed up here. I wrote r cubed. That should have been r squared. But over time, they would have combined to be r cubed d theta. I guess I skipped this. That step in my head, I'm sorry. Anyhow, I can replace these r's now in terms of the theta that I'm integrating over. And I will be m over 2 capital R, which I'm pulling out because it's a constant, r cubed d theta. And the limits will be from 0 to pi to cover the full circle. Oh, excuse me, I'm so sorry. Don't know why I keep doing that. This r cubed can come right on out because it's a constant, so I'm really integrating sine cubed. And after I do that and plug in my limits of integration, so you can look up, or if you feel like integrating this thing, please feel free to go for it. But at the end, what I'll end up with is m r cubed over 2r times 4/3 after I integrate sine cubed from 0 to pi. One of these r's will cancel, one of these 2's will cancel, and that'll give me 2/3 m r cubed. Cool. So again, I didn't prove that this integral was 4/3, but you can prove to yourself. Okay. Spherical shell. So I do have a handout for this, so I'll be putting this online for you guys. And yeah. Once you have the shell, once you have the shell, the moment of inertia of the shell, I can use the shell to make a solid sphere by integrating a bunch of concentric shells. So if I integrate over the moment of inertia of a bunch of hollow shells. Here's the axis of rotation through the center. So let's say here's the similar axis of rotation, but instead of this being hollow, I'm going to fill it up with a bunch of concentric shells to make a solid sphere. I would be integrating over the infinitesimal moment of inertia, of a thin spherical shell, which would look like 2/3 times dm times r squared. So in theory, if you integrate over this, find out what your dm is, find out what your r is, you should be able to find the moment of inertia of a solid sphere listed right here for you as 2/5 mr squared. So maybe you can prove this to yourself. After that, we should spend some time talking about moments of inertia now that we can integrate a few of these. What are the moments of inertia of composite objects? And we'll also spend a little bit of time talking about the moment of inertia of an object on a parallel axis. So let's talk about composite objects. So let's say you have an object here that looks like just a rod, but it's not just a rod, because on the edge of the rod there's a tiny point mass, m. And so let's say this rod is a uniform rod of mass big M and length L, like we've seen before, and we're going to say that it's rotating around this axis of rotation here on its end. So the thing is I don't just have one rod, I have a rod plus a point mass. What's the moment of inertia of a composite object like this? Well, the moment of inertia of both of them is really just the sum of the moment of inertia of the rod plus the moment of inertia of the point mass. Moments of inertia are in general summative, right? We saw that in this form. And so let's say I have the moment of inertia of a rod and I'd sum over all the point masses of the rod, but there's still one more, right, this distance away. I would just be adding it on to the rod according to this sum right here. So moments of inertia are additive. I just keep on adding the more stuff I have. So I already know the moment of inertia of a rod around its end. We found it to be 1/3 ml squared. And the moment of inertia of a point mass is just mr squared. R is the distance away from the axis of rotation. Well, here r is equal to L. So for the composite object, which is just two objects stuck together, I'll have 1/3 ml squared plus little m L squared. That's the full moment of inertia. I could give it a common denominator. To find the moment of inertia. So that's for that composite object. Let's talk about kind of case number 2, which is what is the moment of inertia of an object on a parallel axis. So, for example, let's say I have a spherical shell right here. I know the moment of inertia through its center of mass, right through its geometric center. If this is the axis of rotation, I know its moment of inertia is 2/3 mr squared. We just solved for that. If it has a mass m and a radius of r, and the axis is through its center of mass, or the geometric center of the sphere. But what if I was interested in finding out what is the moment of inertia about a different axis of rotation? So what if I left the sphere here, the spherical shell was right here, but instead I was saying, oh, you're just rotating around this axis of rotation now. How would I find the moment of inertia? How would I find the moment of inertia around this axis? I found it around this axis, and I used a lot of stuff about the, properties of a sphere or a circle in order to solve this problem. But what if I had the same mass and it's no longer around its original axes, but it's around, oops, different color this time, but it's still a spherical shell around, rotating now around this axis? Well, the answer to how do I find the moment of inertia is something called the parallel axis theorem. It says, well, if you know the moment of inertia of an object about its center of mass, you can find the moment of inertia about a parallel axis some distance d away from the center of mass location. So for example, I know the center of mass moment of inertia for the spherical shell is 2/3 r cubed, 2/3 mr cubed. So again, when the axis of rotation is here through the center of mass of the shell, I know the moment of inertia. But if it's rotating around this point, I can find it as long as I'm looking around an axis parallel to the center of mass. Well, for a circle or a sphere or something like that, it's actually not so hard. Here is the center of mass axis, and here is literally an axis parallel to it. You see, they're just exactly parallel with respect to one another. And they should be a distance of d away. The distances separating the axes that are parallel are d. And then I can find the moment of inertia about the parallel axis, which is this one. So this is I parallel. By just saying it's equal to I center of mass times md squared. So here that would be 2/3 mr squared plus md squared. So let's say d is equal to 5 times r here. Then it would be times that mass, that distance of d away, well, 5r squared. And so that is the moment of inertia about this axis as it moves around, rotates. So I would be equal to 2/3 plus 25 mr squared, or giving it a common denominator, 77/3 mr squared. So that's the moment of inertia about the parallel axis d away. Now, I never proved this too because the proof is just long and horrible and boring, but we can use this tool a lot. So, for example, you might ask yourself, well, what if instead in the previous problem I had said, okay, well, what if I, instead of the composite object that I told you I have an axis of rotation here. I have a rod, a uniform rod of length L. And instead of a point mass at the end, I put a spherical shell. Its radius is equal to, let's go with 1/5 L. The question is, what is the moment of inertia of this composite object? Well, the moment of inertia would be the moment of inertia of the rod plus the moment of inertia of the shell. The rod would still be 1/3. Oh, let's say it has a mass m and this one has the same mass m, just for simplicity. The rod would still be 1/3 ml squared, but the shell would be I, the center of mass of the shell, plus md squared, where d is about the parallel axes. Well, the distance away from the center of mass axes is here, d, is going to go ahead and equal to L plus 1/5 L, or 6/5 L. So in total, I would write this as 1/3 ml squared plus 2/3 mr squared plus md squared, where d is 6/5 L squared. And of course I'd replace this R with 1/5 L. And then in total, I would have mL squared 1/3 plus 2/3 times 1/5 squared plus 6/5 squared. And do I want to do that math really quick? I can. Hold on. 1/3. Oh man, I really don't want to. Okay, I can do it. 75. So I'll have here, this will become 25/3 plus 25 75ths plus 2 75ths plus 6/5 squared plus 36 times 3 plus 108 75ths. Gosh, I hope I'm doing this right. That would be the new moment of inertia of a composite object where it's not just a point mass at its end, it's a shell too. Whew. All right. So moments of inertia, people, we can calculate them. And if we don't have to calculate them, that's nice. We'll just look them up on this table, and then we can also use this idea of parallel axis theorem and just for composite objects, just adding them together too. But we should have the ability to derive everything on this table. Okay, so I'll be providing you guys with some handouts. And you'll be seeing this again in the lab and in the homework. Okay, so let's keep going. What do you guys think? Nah, you know what? I'm going to take a little break, and then I'll come back and do the torques. I can feel it. I need a cup of coffee. Okay, so let's take a little break, and we'll come back, and we're going to start working on sum of torques equals to I alpha. And so first we're going to define torque. That's a vector quantity, and it's thought of as a rotational force. And then we're going to find a bunch of torques acting on something, and then we're going to apply it to Newton's law, Newton's second law here for rotating quantities. Okay, so that will be part 2 when we come back. So this other one was part 1. Okay, talk to you soon. Bye.